Chapter 7, Storage. Computer storage, data storage, memory, is technology that consists of components and recording media. It's used to retain or store digital data. It's a core function, primary function, and fundamental component of computers. In practice, almost all computers use a storage hierarchy, which puts fast, expensive, and small storage options closer to the CPU, more easily accessible by the CPU, and slower but larger and cheaper options further away, more slowly, not so easily accessed. Generally, the fast but volatile technologies, volatile means they lose the data when the power turned off. Those are called memory or primary storage. The persistent but slower technologies are referred to as storage or secondary storage. The computer system usually uses its input-output channels to access secondary storage and transfers the desired data that was going to be used immediately into and out of intermediate areas called buffers in primary storage, also memory or RAM. Secondary storage, external memory, auxiliary storage, also differs from primary storage in that it is not directly accessible by the CPU. Secondary storage does not lose data when the device is powered down. Secondary storage is non-volatile. It's also typically 2 orders of magnitude less expensive than primary storage. And modern computer systems typically have 2 orders of magnitude more secondary storage than primary storage. In modern computers, hard disk drives are the most common form of secondary storage, but solid-state drives, SSDs, are fast catching up with it. Some other examples of secondary storage are optical disk drives, flash memory or USB drives, floppy disks, magnetic tape, paper tape, punch cards, standalone RAM disks, and iOmega zip drives. Hard disk drives, HDD, fixed disk, is a data storage device used for storing and retrieving digital information using rigid or hard, rapidly rotating disks, platters, coated with ferromagnetic material. The platters are paired with magnetic heads, read-write heads, arranged on a movable actuator arm. The heads can read and write data from or to the platter surfaces. The surfaces of each of the platters are divided into tracks, and each track is subdivided into a number of sectors. The actuator arm can move relatively quickly to a track where a given data is or to be stored, and when the disk rotates under or over the head, the data is read or written by that head. This technology supports random access for the data. Random access means individual blocks of data can be stored or retrieved in any order, not purely sequential. The time it takes to access a given byte of information on a hard disk is typically a few milliseconds, a few thousandths of a second. By contrast, the time taken to access a byte of information in RAM, primary storage, is measured in nanoseconds, billionths of a second. This illustrates the significant difference in access time between solid-state memory and rotating magnetic storage devices. Access on hard disks is typically about 1,000,000 times slower than access to data in RAM. With disk drives, once the disk read-write head is at the proper position and the data of interest is passing under it, subsequent data on that same track is much faster to access. It takes time to move the head to the proper track, and that time is called seek time. Once it's positioned over the correct track, then one has to wait for the desired data to rotate under the head, and this time is called rotational latency and is much faster than seek time. To reduce seek time and rotational latency, systems are designed to transfer data to and from disks in large contiguous blocks. Sequential access or block access of this type on disks is orders of magnitude faster than random access, and many sophisticated algorithms have been developed to design efficient algorithms based on sequential and block access. The two most common form factors for modern hard disk drives are 3.5-inch for desktop computers and 2.5-inch for laptops. Hard disk drives are connected to the system using standard interface cables, PATA, SATA, USB, SAS. HDDs were introduced by IBM in 1956, and they had become the dominant secondary storage device for general-purpose computers by the early 1960s. HDDs have continuously improved and maintained their dominance into the modern era, although SSDs are challenging this dominance. As in the 1980s, as the beginning of the 1980s, HDDs were a rare and relatively expensive additional feature for a personal computer. But by the late 1980s, the cost of HDDs had reduced to the point where they were standard on all but the very cheapest computers. Most HDDs in the early 1980s were sold to end users as external add-on systems. These subsystems were not sold under drive manufacturer's name, but under subsystem manufacturers' name. Examples were Corvus Systems and Tallgrass Technologies. They were also sold under the name of the computer system, Apple Profile. In 1983, the IBM PCXT came out with standard internal 10 megabyte hard disk drive, and soon thereafter, personal computers with internal hard disk drives were becoming much more common. A random array of inexpensive disks, RAID. When hard disks started coming on the market, initially they were quite expensive, but with greater demand, relatively inexpensive disks started becoming available. Less capacity, not quite as reliable, but much cheaper. People realized then that it was possible to create a system, put together several smaller hard disks instead of one big hard disk. It created a system then that has a lower price than that of a single hard disk, greater reliability. Individual disks might not be quite as reliable, but the combination would be greater reliability and improved access speed. In a RAID system, you can distribute the data across several drives in several different ways. The different algorithms for distribution are called the RAID levels. In the different schemes, different distribution layouts are named, identified as RAID 0, RAID 1, RAID 2, and so on. These levels vary according to the redundancy and performance. Solid-state drives are solid-state storage devices that use integrated circuit assemblies to store data persistently. An SSD can function as a secondary storage in a hierarchy of computer storage. SSDs, solid-state devices, solid-state disks, even though they don't have any spinning disk, they don't have any movable rewrite heads. Compared with the electromechanical drives, SSDs are typically more resistant to physical shock. They are quieter and faster. Initially, they were relatively expensive, as any new technology is, but as their costs have come down, they are taking over for standard hard drives in desktop and laptops. They're also a solution for applications that don't require a great deal of storage. Since SSDs were first released, major improvements have come in prices. Prices have decreased and storage capacities have increased. SSDs with capacities over 4 terabytes are now available for home computers. Optical storage is a storage of data on an optically readable medium. Rotating optical storage devices, like CDs and DVD drives, have longer access times than do hard disk drives. The most common optical media are CD, DVD, and Blu-ray. CDs store about 300,000 pages of text, or roughly 700 megabytes. DVDs are commonly used for movies and hold about 4.7 gigabytes of memory. Blu-ray has 5 times the storage of a DVD and is used for high-definition movies. On a single layer disc, Blu-ray can hold 25 gigabytes of data, and on a dual layer disc can hold 9 hours of HD movies or 50 gigabytes of data. Optical discs can be used to back up relatively small volumes of data. But for backing up entire hard disk drives, the relatively slow access times for optical drives makes them impractical. Large backups are often made on external hard disk drives, since they have much faster access times and the price of these devices has dropped to where they are competitive. Magnetic tapes are also used for backups, secondary storage. A USB flash drive is a data storage device that includes flash memory with an integrated USB interface. USB flash drives are typically removable and rewritable and physically much smaller than an optical disk. As of March 2016, flash drives with anywhere from 8 to 256 gigabytes were sold, and less frequently 512 gigabytes and 1 terabyte units. Storage capacities as large as 2 terabytes are now easily available. Flash drives are small, fast, they have no moving parts, they're relatively durable and quite reliable. Additionally, they are immune to electromagnetic interference and are not subject to surface scratches. There are several types of storage media that used to be commonly used, but are no longer in wide use. Some of these are floppy disks, magnetic tape, paper tape, punch cards, and zip disks. A floppy disk is a kind of disk storage composed of a thin plastic disk covered with ferromagnetic material, which forms a storage medium, can be magnetized, put data in magnetic form. These are sealed in rectangular plastic enclosures. They are read and written by a floppy disk drive, or FDD. The earliest Floppy disks were 8 inches wide. Later, much more commonly used were 5.25 inch disks. Then came 3.5 inch disks, and later even smaller. Magnetic tape is a medium for magnetic recording made of thin magnetizable coating on a long, narrow strip of plastic film. It was a key primary technology in the early computer development, allowing huge amounts of data to be mechanically stored, created, stored, and reread, rapidly accessed. Tape is still a viable alternative for some situations due to its low cost per bit for storage. This is a big advantage when you're dealing with large amounts of data. The highest capacity tape media are on the same order as the very largest available disk drives, which was on the order of 5 terabytes in 2011. Tape is historically cheap enough, it has a big enough cost advantage over disk storage to make it a viable product for backup, especially where media removability is necessary. Punched paper tape, perforated paper tape, is a form of data storage, consists of long strips of paper with holes punched in to code data. It's pretty much obsolete, but it was once widely used. During much of the 20th century, it was used for teleprinter communication and somewhat later for input for computers of the 50s and 60s. Even later, it was adapted for use as a storage media for mini computers. Punch cards were widely used through much of the 20th century in what came to be known as data processing industry, where specialized and increasingly complex machines organized into data processing systems used punch cards for data input, output, and storage. Herman Hollerith invented the recording of data on a media that could be read by a machine. Prior uses of machine media had been for control, but not for data. Herman Hollerith was busy designing a system to use for the census, and he initially experimented with paper tape, but settled on punch cards. He developed punch card data processing technology for the 1890 U.S. Census and formed a company that was later to become known as IBM. Punch card technology developed into a major tool for business data processing. By 1950, the IBM punch card had become the primary ubiquitous in the industry and government. Most early digital computers used punch cards. These were often prepared using punch card machines, key punch machines, as they used these punch cards for the primary medium for input, both for programs and for data. The zip drive is a medium to high capacity, high at that time anyway, removable floppy disk storage system that was introduced by Omega in 1994. This format became the most popular of a group of super floppy products, floppy better than floppy disks, which filled a niche in the late 1990s for higher capacity portable storage of data. It never became quite popular enough to replace the 3.5-inch floppy disk. Later versions of the zip drive matched the capacity available on rewritable CDs, but were never big enough to displace or compete with rewritable DVDs. The zip drives pretty much went out of favor for mass portable storage. Some organizations have started renting storage to subscribers. This system is referred to as cloud storage or storage in the cloud. The idea is that people or organizations buy or lease storage capacities from the providers, store the user or organization or application data for them. The cloud storage providers then are responsible for keeping the data available and accessible, and that they keeping it protected and running. Cloud storage services can be accessed through Cloud Computer Service or Web Service Application Programming Interface, API, or applications that utilize such an API. Very often, these cloud storage providers also provide application software. Hosted software differs from typical software in its installation and its accessibility. Unlike most software, which is housed on the user's machine, hosted software related data processing and computing is performed on the remote host server. So the software is on the server and it runs on the server. End users access their data through the web browser. Generally, hosted software is provided as a service to end users. The users are billed monthly on a pay-per-use or per license fee billing method. Because all the programs are installed at the provider's location, they're managed, upgraded, and patched by the provider, ensuring then that the users always have access to updated, bug-free versions of the software they use, since it is installed and maintained by professionals. the early days of computing, storage was limited and expensive, and they developed a number of techniques and programs to implement these techniques to compress files and collections of files. The idea is to create a file having an accurate representation of the information, original information, but requiring less storage space. The most widely used of the programs create compressed files with extensions .zip and .rar. Since the early days, the price of storage has come down, major reduction. Capacities have increased radically, but data compression has continued to be extremely important. Data communication is becoming more and more important, and the speed at which data can be transferred is critical. Obviously, if you can compress the data using fewer bits than one would normally use, then the result can be transmitted in less time. It can be transmitted faster. There are two general classes of data compression techniques: lossless compression and lossy compression. With lossless compression, the data is reduced in size, but the technique produces a file that can be decompressed to exactly the original form. Lossless, then, compression does not lose any information in the process of compressing and decompressing. This is essential for files that have to be exactly, that cannot lose any information. Text file, any change changes the content of what it says. A program, any change, just a single bit, is going to change what the program does when it's executed. On the other hand, there are situations where some loss of information is acceptable. With lossy compression, you can create compressed file sizes much smaller than one can with lossless techniques. This lossy formats are suitable for certain kinds of file types where a few details can be ignored, differences can be ignored. Audio files, a minimal change in an audio file is probably not going to be perceived by the human ear. Video files, a small change in one frame of a video file, it goes by so fast you're not going to notice it. Most kinds of graphics can tolerate small losses of information. In situations where multiple people, multiple entities have access to the same storage device, generally there's going to have to be some restrictions on who can access, which entities can access which data. In Unix system, the kinds of access are identified as read, write, and execute. The Windows systems usually have similar access definitions, but they also have a couple of other controls. A user with read access can access, read, and make copies of the contents of a file, but is not allowed to make changes in the content of the file. A user with write access can make changes to the content of the file. If a file happens to be an executable program, then our user needs execute access to be able to run the program. In most computer systems, access privileges are assigned by the file creators and or system administrators on a ad hoc basis, file by file. On large complex systems, however, it's important to have a standardized policy for assigning access privileges. These standardized policies should be designed according to some access control model. There are three widely used access control models: the Bell-LaPadula model, the Biba model, and the Chinese wall model. Each of these models emphasizes a different type of security. Each is appropriate for a different situation. The primary goal of a Bell-LaPadula security model is to prevent users from gaining access to unauthorized information. Access levels are arranged hierarchically. Users and data files are assigned access levels. Typical access values tend to be motivated by military-type security: top secret, secret, confidential, unclassified. A user can read data at or below his or her access level, but is prohibited from reading data from higher levels. Data produced by a user is assigned his or her access level or higher, and users cannot modify files with access levels below their own. Summarized as read down, write up. Read lower level security, but cannot write higher level security. But cannot write lower. It's designed to prevent low-level users from accessing high-level data and prevent users from transferring high security data to where it might be accessed by users with lower security privileges. The Biba model, while the Bell-LaPadula system is concerned with inappropriate disclosure of information, the Biba model is ensured and aims at ensuring integrity of data. Like Bill Lapadula, the BEMA model is hierarchical, with information at higher level being considered more trustworthy and access implemented on a read up, write down basis. Users can access information at or above their own level. They can modify data that's at or below their own level. High level users cannot access the less reliable information, which they could potentially contaminate high-level files with unreliable data. Users with access to less reliable information cannot move that information to higher, more reliable levels. The situation with a BEMA model might be appropriate would be a software development company. Such a company might classify their collections of data as production level, beta level, alpha level. Production level software would have been rigorously tested and would generally be considered reliable. All of the company's programmers can read the production level code and incorporate parts of it into their own projects, since it's quite reliable. Programmers can read higher level stuff, but only the most senior and most trusted programmers would be allowed to make changes in the production level code. Beta level software would have passed through some degree of testing, but are still not considered completely trustworthy. Sections of code from beta level software could be used in the alpha level projects and other beta level projects, but are not completely trusted, should not be incorporated into production level software. Alpha level software has not been tested, at least not well enough to be elevated to beta status. It's even less trustworthy than beta. Alpha level developers can read production and beta level software and incorporate ideas into their own projects, but they're not allowed to insert untested ideas into more trusted software. Chinese wall security model divides the data into mutually exclusive collections, and a given user would be permitted to access to one and only one of these collections. This model is appropriate for situations like that of a large legal firm representing numerous clients. Lawyers representing one client would not be allowed to access records relating to other clients with potentially competing interests.